Our next piece here is to discuss, I want to review just a little bit more about this area so far function. This is from the second part of the fundamental theorem of calculus. And so I want to talk just a little bit about this because that's going to lead into really the next big topic. We have two big notions left so far in the semester. We'll get through this week. And this is sort of the stepping stone to get to the first of them. It's this area so far function. And so I'm just going to pick a nice easy function to play with. I have g of t is equal to t. So this is just the constant function g of t equals t, this diagonal line that passes through the origin. And this area so far function from the second part of the fundamental theorem looks like this. Now, this bottom constant is permitted to be anything. I'm going to choose something easy. I'm going to choose it to be 0. It is not required that this be 0. We can, in fact, later on we'll consider this to be 1 or some other value. But for now, since this function actually passes through 0, we're going to choose 0 here. And I'm going to take this function to be, I'm going to move this over a little bit, 0 to x of t dt. This is called an area so far function. And the reason for that notion, the reason for that nomenclature is this. Suppose we want to evaluate this expression at a particular value for x. And so what I'm going to do is this. I'm going to make a little chart here, x, and I'm going to say this is the integral from 0 to x of t dt. You do not need to be able to reproduce this. I'm just going to discuss this idea so you have maybe a little bit better feel for what's going to be happening here. Now, if I choose x to be any particular value, suppose I choose x to be 0. The question is, what is this value if I choose x to be 0? Well, this is the integral from 0 to 0 of t dt. Now, this is a continuous and differentiable function, so we don't have any problems about existing. We know we have no holes, no jumps, no vertical asymptotes, and no cusps. But if the endpoints if the two limits of integration are the same number, we know that's equal to 0. So really what I have here is 0, 0. But look, if I choose x to be 1, what does that represent in the larger picture? Well, it is the integral from 0 to 1 of t dt. What is that? Well, find antiderivative of t. Antiderivative of t is t over 2. T squared over 2. And we're choosing the constant to be 0. And we evaluate that from 0 to 1. When you evaluate at the top value, that's 1 squared over 2 is 1/2. Minus evaluate at the lower limit, that's 0 squared over 2, that's 0. So that's 1/2. If 1 is the input, 1/2 is the output. What does that mean? It means if I choose x to be 1, that corresponds to this is 0, this is 1, and I'm finding the area from 0 to 1 underneath this green curve. I'm finding the area of that triangle. And we can demonstrate, we can prove that this triangle matches this value. This is the area of that triangle, the area so far. Well, the area of a triangle is 1/2 the base times the height, and we know this base is 1, this height is 1. So we know the area of this triangle is 1/2 times the base times the height, which is 1/2. And sure enough, when we evaluate this expression, this gives us the area from 0 to 1. Now, suppose I choose a different value. Suppose I choose x to be 2. What is the result of that choice? Well, we get 0 to 2, t dt. The antiderivative has not changed. It is still t squared over 2, but now we're evaluating it from 0 to 2, which is 2 squared over 2. 2 squared over 2 is 4 over 2. Minus, evaluate at 0. Well, this is convenient. It's always going to be 0. Well, 4 over 2 is 2. Now, what does that correspond to? When x is equal to 2, that now corresponds to the area. As x gets larger and larger, as I slide x from 0 to 1 to 2 as we move out. As this right limit, the upper limit of integration gets larger and larger, we're sliding from left to right, and we're getting more and more and more of this area. We now have the area so far. That's where this name comes from. The area so far, and I'm claiming that to be 2. Now we know how to find that. We know how to find the area is 1/2 the base, which is 2, times the height. Because this is a 45-degree angle, we know this is an isosceles triangle. And so if this is 2, this is 2. So it's 1/2 times the base times the height. This 1/2 cancels with this 2, so this is 2, and sure enough, that's what the area so far is. That's what we mean when we say area so far, as that's the behavior of this variety of function. Now, there's nothing magic about this particular function. This can be done with any appropriately defined function. It's the area so far, from 0 to 2. This is a function of x. As this upper limit of integration gets larger and larger and larger, you gain more and more and more of this area. And this is a function. One input produces one output. One input produces one output. One input produces one output. And so it doesn't matter what value of x we choose. We could choose x equal to 10, and that would give us, this would give us the area under this curve all the way out to 10. Now we can compute that because we know the area of a triangle. That's going to be 10 for the base and 10 for the height. So 1/2 times base times height. Well, 1/2 of 10 is 5. So that's going to work out to be 50. So if I do this integral from 0 to 10, here, let's move it over here. If I do the integral from 0 to 10 of t dt, that stinking better work out to be 50. And sure enough, the antiderivative hasn't changed. It's still t squared over 2. Evaluated from 0 to 10, and that's evaluated at the top, so that's 10 squared over 2 minus evaluated 0 is still 0. And so that is 10 squared is 100 over 2 is 50, and sure enough, that's what that value works out to be. So that's what we mean by an area so far function. You are not required to have it to be this function. You may use any function you like here, any function of t you like. You are not required to have it start at 0. This can start at any particular value. I started at 0 because it made finding the areas of these triangles easier. If we had started at 1, that means we're now starting at this value and going to the right, which means now we're finding areas of trapezoids. It's a little more challenging to find it geometrically, but the procedure calculus-wise could be done in exactly the same way. The point is this. This is a function of x. Given an x, you produce an output. Given an x, you produce an output. This is a function of x. And this is the key result from the fundamental theorem. It says this. So let's see if we can, 0 goes to 0, 1 goes to 1/2, 2 goes to 2, 10 goes to 50. So this actually is a function of x. The fundamental theorem says this: if you want the derivative of this function, the fundamental theorem says if you have one of these area so far functions, then the derivative with respect to x, with respect to this upper limit variable of, and this lower limit could be 0, this lower limit could be 1. The lower limit is allowed to be anything. And this is f of t. This is allowed to be any function dt. I'll call this g of t. I'm going to use f twice. This is allowed to be any function. The derivative of an area so far function with respect to x is given by g of x. It is this function evaluated at the upper limit. What is the derivative of this function? The derivative of this function is x. That's what that is. So that's this piece from the fundamental theorem. The area so far function and the derivative of an area so far function is take this function, substitute x in for t. That is the derivative of this area so far function. Now, for now, that's just a bald fact. The next thing we're going to look at is a particular one of these, which has some particular properties and behaves in a specific way, and that's going to work out to be a function that you should be sort of familiar with.